We'll start the solutions from A, B, and then we'll go to C. I don't know if all the solutions would pass the system tests, but as of now I'm giving the solutions. Problem A was an easy problem. In this, it is given that we will have a binary string, right? We'll have a binary string. Let us have a binary string like this, having some like this, any string, a binary string, and we need to rearrange it to eradicate any palindrome of length greater than or equal to 2. Fine. So we know that if we have any palindrome, if we don't have any palindrome of lengths 2 and 3, we don't have any palindrome of length 2 and 3, we won't have any palindromes, right? So if we have so basically the thing is that let's try to find if we have any string of length 3 which doesn't have any palindrome. Maybe if we have a 0 0 0, this is a palindrome. If we have 0 1 0, this is a palindrome of length 3. If we have 0 1 1, this has a palindrome of length 2. This also has a palindrome of length 2 and also of length 3. If we have is there any new case like 1 1 0 is just a repetition of the above case? I can have 1 1 1, I can have 0 0 1, I can have like all the possibilities. So if the string is of length 3, there is no such string which is palindrome free. Fine. That means like if I have any string of length equals to 3, so the answer will always be no. Fine. Because I cannot have any string of length 3 which is not having any palindrome of length greater than or equal to 2. Fine. So but so then if I have string length greater than 3, then directly it will become no, because every string of length greater than 3 has a substring of length 3, right? So that substring, if that substring always contains a palindrome, then a string of bigger length will also contain a palindrome, right? I mean to say, it is very trivial to think, but if I have like a string of length 5, this part is a substring of length 3, and this will always have a palindrome. So the whole string will also have a palindrome, right? So by that I can prove that I will always have a palindrome in string if length is greater than or equal to 3, right? So the answer is always no for these. If length is 2, so there are two cases. Either I have 1 0 or 0 1, or I have 1 1 and 0 0. For these the answer is no, because these themselves are palindrome. For this the answer is yes. Fine. Because both cannot have a palindrome of length greater than or equal to 2. And if length is equal to 1, the answer is no, because we are asked, this itself is a palindrome technically, but we asked palindromes of length greater than or equal to 2. So this doesn't have a palindrome. So the answer is the answer is yes. Fine. So that was A. Coding A is very easy. Let me show you my code. Fine. Just take the inputs, and if This part you can ignore because I had written this for some other case, but forgot to delete it. Just see this part directly. Yeah, if n is less than equal to 2 and s0 is not equal to s1, then yes, otherwise no. Fine. Let's go to problem B. So problem B is a good problem according to me. In problem B, it was said that we have to rearrange. Okay, let me explain problem B first. Okay, we have B. Fine. We have numbers from 0 to some n minus 1. We have been given a number s, a number n, right? Yeah. And then that means we have a set of numbers from 0, 1, 2, 3 up till n minus 1. Fine. And then we need to again rearrange these numbers. We have to rearrange these numbers in such a way that for any two, let's suppose the rearrangement, after rearrangement the array becomes A. Okay, so for any I between 0 to n minus 1, 0 to n minus 2, I should have okay, I will have AI and XOR of AI plus 1, right? So the maximum of all AI XOR AI minus 1, AI plus 1, this should be the minimum. Fine. This should be minimum. XOR of any consecutive pairs, the maximum XOR which we can see should be minimum, right? So how can we solve this? So if I have numbers, let's suppose I have numbers from up till I have some numbers up till, let's say 13. Fine. So I will have numbers like this. One like this. I will have numbers. Then at some place I will get 8. I will get 7 first, and then I will have 8. Then 8. Then 9. Then 10. Then 11. And then 12. And then 13, right? So what we can see here is that if I take any number A which is greater than 8, greater than or equal to 8, and I take a number B which is less than 8, so A XOR B will always be greater than equal to 8. Why? It is true because of the fact that the most significant bit of A, this one, will be 1, and the most significant bit, the most significant bit of A, this one, will be at the 4th position here, and the bit at the 4th position for B will be always 0. So at the 4th position I will always get a set bit. Fine. So for example, A will become like 1 and then some numbers, the binary representation of A, and the binary representation of B will be something like this. So their XOR will always be like this. Fine. So therefore A XOR B will always be greater than 8. Okay. Now if A XOR B is always greater than equal to 8, and I can always have two numbers like U XOR V. If U and V both are less than 8, then U XOR V will always be less than 8. Okay. So if I choose any two numbers from this range, their XOR won't add up to become 8. Okay. And if I choose any two numbers from this range, okay, their XOR, so any two numbers from this range will have XOR less than 8. Any two numbers from this range will also have XOR less than 8. Why? because if I choose both numbers from this range, both will have set bit at the fourth place, right? So they will cancel each other and XOR will be less than 8. Only the thing is that if I have one number from this one number from this one, so then their XOR will be greater than 8, right? So we just need to minimize this XOR. Fine. At some place we can't have like when we arrange the numbers, we will have some numbers less than 8, some numbers greater than 8. If the number is like for the case of 13, right, I'm telling, we will have some numbers less than 8, some numbers greater than 8, and so at some place we will have two numbers where one is greater than 8 and other is less than 8. At that place we will have XOR greater than equal to 8. At all other places we might have XOR less than equal to 8, so we just have to minimize this XOR, right? So how to minimize this XOR? Fine, this is the thing now. So to minimize this XOR, what we can do is that we can just group all the numbers from 8. Okay, 8 and greater numbers, the numbers which are 8 and above can come in one group, the numbers which are less than 8 will come in other group, and then only one boundary will be there, one separation place will be there where they will be separated. At that place we can put a number which will make that XOR, that place XOR exactly equal to 8. Like when I write, it will become more, it will make more sense. For 13 I can do it like this. Okay, I can start with 8, 9, 10, 11, 12, 13, right? Then I can just put a 5. I can just put like some numbers, the other group of numbers. We'll see how will we arrange those numbers. Some other group of numbers like 0, 1, 2, 3, 4, 5, 6 and 7, right? So each number, these two XORs are less than 8, these two XORs are less than 8, these both have XORs less than 8, these both have XOR less than 8, these both have XOR less than 8. Only these two numbers have XOR greater than 8. Fine. These two have less than 8, these two have less than 8, all of them have less than 8. So can I pick one number from these, from this array, and make that place that number in just in front of 13, so that we get the XOR exactly equal to 8, because it is always greater than equal to 8, right? So if 13 is 1101, right? If 13 is 1101, I will always have, because I have all the numbers, all the occurrences of 13, of numbers from 0 to 13, I will always for sure have a number which will have 0 here and the exactly same numbers here, right? And which is 5 in this case, if this is 13. So their XOR will come out to be exact 8, always. Fine. And we know that if a number is greater than 13 and the other number is less than if the number is greater than 8 and the other number is less than 8, their XORs will always be greater than equal to 8, right? So the best is like to make it exactly equal to 8, and which is always possible by choosing a number, just by choosing a number which has this bit, the most significant bit 0 and the other bits equal, right? Fine. So the ideal arrangement here would become, let me just show you what is the ideal arrangement. I'll just pick up this 5 and place it in place of 13, right? 8, 9, 10, 11, 12, 13, and then I'll place a 5 and the rest numbers 0, 1, 2, 3, 4, 6 and 7, right? So this will be the best arrangement possible, right? This will become the best arrangement, and here XOR will be 8 and all these XORs will be less than 8 and all these XORs will also be less than 8. Fine. So basically I could have also done this thing if I would have placed this in the other order, 13, 12, 11, 10, 9, 8 and then 0, 1, 2, 3, 4, 5, 6, 7. This would also have given me the correct answer, right? Because all these XORs are less than 8, all these XORs are less than 8, and this XOR is exactly equal to 8, right? So why am I breaking at 8? Now the question might be this, that why am I breaking at 8? Because we will have to break at the number where the most significant bit changes from 0 to 1. That is, and where it will change, this the number will be a power of 2. Fine, the number will be a power of 2. So the break point will be where the number which is like the greatest number, which is small, which is the power of 2 and smaller than n. Fine. So for 13 we will have 8, for 21 we will have 16. The highest power of 2 which is smaller than n, that will be the breakpoint. So finally what I can conclude is that I think this pattern is the easier one. What we can do is that just start from n minus 1, go to n minus 2, and let's suppose we have a breakpoint. That means the highest number which is the power of 2 and less than n. Okay, let's suppose that number is p. Okay, which will technically be log base 2 of n minus 1, and if you want to calculate this in C++, you will have to do like p is equal to log of n minus 1 over log 2, and then yeah, this is the number of digits in p, right? This is the number of digits in p, and then you just shift, take this as like this. Fine, sorry, yeah, you can do just p is equal to 1 shift operator p. That is like, just raise this power to the p. Okay, or even if I'm like little bit off here, you can just check. So the series will become n minus 1, n minus 2, up till you have to go till p, and then start from 0, 1, 2, up till p minus 1. This is the series. Fine, yes. So that was B. Let's go to problem C. Problem C. So problem C is a very good problem again. Problem C. In problem C we have two numbers A and B. Fine. In one operation our ultimate aim is to make A is equal to B. Fine. This is our aim. In one operation, what I can do is that either I can do A plus plus, or I can do B plus plus, or I can replace A with A or B. Fine. A or B. So this question actually requires you a little bit practice in bit operators and bitwise questions using bitwise logics, but still I would like to explain you how I did this problem. So basically what can happen is that, let's suppose I have some A as this number. Okay, this is A, and I have B. Okay, this is B. So basically what we need to do is that we need to make A equal to B, right? So what we can do is that we always know that, first of all, we know that A or B is always greater than maximum of A comma B, right? That means if A was smaller than B, after doing the operation A will become bigger than B. Fine. So if we add some number of if you do the first operation some number of times, like increment A some number of times, and then apply the OR operation, and then again we are required to, okay, let me just fine, we have these three operations. What we can do is that we can try to increment a some number of times. We can try to increment a some number of times, that is like some x amount of times. Fine. Then do, first you do this, then you do this, a is equal to a or b, and then you can do, and then you can increase b some y amount of times to make it equal, right? Even y can be greater than equal to 0, x can be greater than equal to 0. Fine. This is not fine. Or what we can do is that in the other operation, like I'm just telling how can we approach the problem. Either we can approach in this way, first increase a some amount of times and then do or, and then increment b some amount of times. Or you can do is that, or what you can do is increment b some amount of times, right? Some amount of times, then do a is equal to a or b, and then increment a some amount of times, right? Fine. So you might ask, why don't we increment a some amount of times, then b in some amount of times, and then take the or? So the thing is that it is always okay. So the thing is that it is always better if we try to do only one number, if we try to only focus on one number and take the or afterwards, and then increment, and then take the or and then increment the other number, right? So if I have, yes, so what we can just finally do, I don't actually have a very solid proof on why only we have to do in this order, in these two orders, but actually it worked for me in the contest, and I had done some long bitwise calculations which you can see in the stream, and after that I came up with this idea. Okay, and now what we can do is that we can just iterate on this x, right? We can use a loop. I'll show you my code. Okay, first I'll explain and then I'll show you my code. I can just iterate on this x. Okay, from, we can apply a loop on this x from 0 to b minus a. Fine. And then check, how many y's do we require, right? How many y's do we require? That is, if we have done already, if we have already done some x number of operations, so now a will become a plus x or b. Fine. And then the number of operations y will just be the new a, let's call this new a, the new a minus b. Fine. And in this case we can do, we loop y from 0 to, we can loop y from 0 to, what I did is like, how many iterations, like till how many, what is the maximum value of y, what we can, where we can go. The maximum value of y is basically, if y is something, if b is something like this, if I iterate till this number 1 and then same b, just increment this 1. Fine. I will always cover all the cases, right, of this part. For this part I will cover all the cases for this part, and then after covering all the cases from this part, I will always end up matching this part with A, with this part with the same corresponding part of A, and where the ORs will become equal. Fine. So always they will be, always it will be better to, I will have my answer until I loop till here, right? So loop till 2 to the power digits in B plus 1 plus B. Fine. And the new B, so here also we have a new A, which is equal to just B plus Y or A, and then X required, the required amount of X is like new A minus B plus Y, and just keep answer is equal to minimum of answer comma the operations required now, and here as well answer is equal to minimum of answer comma operations required now, and then we are done finally. Fine. So these were the solutions of the contest of the problems ABC. I think you might have not got what, you might have not fully got how C has been done, but I guess if you see the, if you like just see the solutions what I told and like give a think of by yourself, you will develop the logic for C, and also read the editorials and feel free to see other solutions which might have explained better. But anyhow, this was what I could have, what I could explain in C. This was B and A. I hope you enjoyed the video, and bye bye.